So, with this idea of Gram-Schmidt orthogonalization or orthonormalization, when you consider the norm to be 1, we land up with an interesting concept of how to approximate a signal linearly in a signal space. Okay. So, the question is, we would like a signal S of t to be a weighted linear sum of some basis signals, n basis signals k equals 1 to n. That is, we want an approximation to S of t which is in this form. S hat of t is summation k equals 1 to n Sk Fk of t. So, as I said, the question is how can we do this? What is the basis Fk of t? How do we choose the basis Fk of t, right, and what should be these components Sk, right. So, this is one of the questions that we get. So, we will see this as a minimization of a square error procedure to compute these coefficients Sk which appear before the basis Fk of t, and this automatically, and the second question is basically how do we generate Fk of t given a set of signals S1, S2, S3, S4, so on. I am given a collection of signals and I want to get an orthonormal basis to these set of signals. That is the first question, and given those components how can I get Sk. Basically think about it as a projection, but we will see if this really is how this translates to this projection. We will think about in two different ways. So, for this let us formulate the square error, right. At this moment I have not assumed any stochasticity in the signal, and if you bring in stochasticity then you have to kind of average it over the distribution, you have to think about some measure over the distribution of the random variables in the signal, but I am just ignoring this at the moment. So, the square error is basically from looking at the error of the signal, which is basically S of t is my original signal, S hat of t is my linear approximation to this signal in terms of these basis functions, right, and I want to take the square deviation, integrate this signal from minus infinity to plus infinity. It could be just, the limits could be just from minus pi to pi or 0 to 2 pi or whatever finite limits you want to consider, but without loss of generality I just wrote minus infinity to plus infinity. Now, we want to minimize this square error. So, now once you set this up, setting up this objective is important. I mean, like in any optimization problem, right, you have to have some objective. Why the square error is a question, right. Why not the cube error, why not the power 4 error. Square error has a number of interesting properties, and one of them is it is a quadratic function. So, therefore, if you want to optimize something, you land up with a unique solution. It is a convex. You have to think about it in terms of the geometry, right. the square error is basically a quadratic surface, it is a parabola. So, and if you think about the parabola, you have only one minimum point. So, therefore, if you apply your calculus, if you want to solve for some optimal parameters over the surface, you can uniquely get to that point, unless if the surface is more complicated, where you will have to figure out you know what should be the global minima of that surface, etc. So, this is these ideas you will sense it in optimization, but in signal processing heavily people have followed square distortion, square error, right, and we will see this how this trick is going to be useful for us. Now, once we set this up as a square error, and this square error is just time averaged over this you know just integrate the square. I mean I am not even talking, I am saying it is energy, not even just scaling here by the time and taking the limit as the time goes to infinity, right. I have not even defined it in terms of power, just the energy here. So, E is basically integral minus infinity to plus infinity S of t minus I just drop in plug 1 in 2. So, when I plug 1 in 2, I have the summa k equals 1 to capital N Sk Fkt, take the square dt. Now, this is very straightforward, though it looks like integral and some summation inside. So, we just have to apply calculus. We take the derivative with respect to some s k, right, and some s k I have to take the derivative. So, what do I get? So, I have 2 times. So, maybe I could make this S n here just so that since I have some k's there in the last slide. So, summation goes from k equals 1 to n, maybe I take the derivative with respect to n, this is without loss of any generality. So, I take the derivative of the error with respect to S n, right. So, basically I have minus infinity to plus infinity S of t minus summa k equals 1 to n capital N Sk Fkt, right, this is what I have, and then I have to take a partial derivative of this argument here with respect to Sn, right. So, if I have to take with respect to Sn, I deliberately avoided the Sk here. So, this is something that you have to be careful about when you do if you started off with some indices going from k equals 1 to n, maybe use some other index here that you would want to take the derivative with respect to, right. So, now we have so only that with f suffix n will be there and rest will just vanish because it is a partial derivative, right. So, basically you just land up with Fn of t dt, and this has to be set to 0. Now, I get a very straightforward equation here, right. So, now integral minus infinity to plus infinity, the 2 will just cancel out, you do not have to worry about. So, S of t with f n t f suffix n t dt is now if you take the integral here, So, you are going to have sigma. So, now you take Fk with Fn, if you have them to be orthogonal to each other, then they just you know they Fn f for k not equal to n, they vanish, and for k equal to n they exist, right. So, basically I will write it in this form. This is going to be, so you are going to have an Sk Sn essentially, and this is basically Fn square dt, right. If these signals are orthogonal, then, but now if you want them to be orthonormal, right, I would say this is Sn, this beast is just going to be Fn square dt, this could be 1, because of orthonormality. Things are now very simple. It is just the inner product of this signal St with Fnt. This is how we would compute Sn. Which also sort of makes sense if you thought about represent, this is basically giving you the coordinate of that of the signal S of t in terms of these bases f and t, f suffix n t, clear, is one way of looking at it. The other way is just sort of recasting it in terms of a square error, taking these partial derivatives and then computing what you need to compute. Okay. Now, our job is not yet done, because we need to compute the squared error, right, because we said we are approximating it as a weighted linear sum of some orthogonal signals, right, orthonormal signals, and now we want to compute what our squared error is. So, E, if you just expand this out, is a square of t dt, right. Just take s of t minus this, you have this quantity here, right, you have this equation 2, and you just have to expand equation I mean equation 2 in this form here, basically you just have to expand this out. So, you will have a square t s of t with this term here, and then this whole term squared, right, a minus b whole square, you just have to expand this out. So, this is minus 2 times integral minus infinity to plus infinity s of t summa k equals 1 to n capital N s k fkt dt plus integral minus infinity to plus infinity summa k equals 1 to n sum sk fkt times sum L equals 1 to n SL FLT dt. So what I did, instead of taking this whole square, I just expressed it as two different summations. It is just the same, just the running variable here is k and l. So you do not want to have k equals 1 to n, another k equals 1 to n, just replace it with one, k equals 1 to n, j equals 1 to n, and we will see how this basically simplifies. So this square error, now just focus on this term here, right. This term is just the energy in the signal Es, right. Energy in the signal is basically square of the signal, you know, integral minus in plus infinity s square t dt is energy in the signal. Now this is interesting because now assume that you can exchange the summation and the integral, and you have to be careful when you could exchange the summation and the integral. I mean, this is a finite support here, sigma of k equals 1 to n. So this is finite, so therefore you could exchange this. There is Tonelli's theorem which basically gives you a condition how you could exchange these double sums etc. from analysis. So assuming such an exchange is possible, right. So now what we have to think about is you have k equals 1 to n sk, and think about st with fkt. So it is basically the projection of the signal st with fkt summed for all the components k equals 1 to n, right. So you just land up with sigma k equals 1 to n, this sk will be there, and when you take this integral inner product sk s of t with fkt, you get sk there. Right. Because that is our definition, right. If you just go back here, this is our definition. Sn is basically the inner product of the signal s of t with fnt. So therefore this step is straightforward. So bear in mind I have considered all real coordinates here. So therefore if it is complex, you will have to be slightly careful what you have to do here. So basically this term can be simplified as this, and we have the last term. So the last term is also not too hard. So first we will just pull the summations out, k equals 1 to n sum l equals 1 to n, I pull out this. So I have sk, I have s suffix l, right. I just get this integral. So you have to be extremely careful when you exchange the summations and integrals. I mean in signal processing we just take it for granted to do this, but again the roots to this is analysis. So if you did a math course in analysis 1 or 2, you will appreciate all these subtle aspects of exchanging limits and exchanging integrals, exchanging summations or summation and integrals etc. So I won't delve with those things because it is part of analysis, a separate course. So we will end up with this integral minus infinity to plus infinity fk of t fl of t dt. Now we are home for good. Right. I think I would just want to skip this arrow here because I did not write this term. So now you can basically simplify simplify this, because this will vanish if they are if they are orthonormal, right. So, therefore, integral when k equals L, this integral would exist, else it would just vanish for k not equal to L. So, therefore, this is basically k equals 1 to n sk square. So, I just had to take a 2 here with that I missed. So, now our error is basically the energy in the signal minus sum k equals 1 to capital N sk square. And I think you have to ponder about it at this moment as to why this result is interesting. Now, if you had these signals F1, F2, F3, right, you can consider them so if you had the signals F1, F2, so F1t, F2t, F3t, so on, you can, and we said they are mutually orthogonal and they are orthonormal, it is an orthonormal basis. So, therefore, you can write it like this. So, this S hat of t, I mean I am assuming 3 components here. I mean if you think about n such basis, you have to think about it in n dimensional signal space. So, my S hat could be some signal that is a point in this space. That means it will have some component of F1, some component of F2, some component of F3, right, and that is how I would represent that signal as a weighted sum of these bases, right. And the error that I do in such an approximation is now what is basically the energy in the signal, which is Es, minus summation k equals 1 to n, 1 to capital N sk square. This is basically the norm square of this vector representation. This is square norm of S hat of t in the signal space. I think it is a pretty interesting result. I mean it seems intuitive that if you have an over complete basis or if it is a complete basis, this error should be 0. If it is a complete basis, the error should be 0. If it is not a complete basis, you have a residual error, right. So, now the questions that one has to ask is, can we construct a complete basis for a particular signal set? Is that possible? What sort of basis? What sort of properties? And this is one of the important questions in signal representation, be it wedgelets, be it wavelets, be it DCT, be it any transform. You can come up with your own set of functions, set of basis functions. So, provided this is the first property that you will have to satisfy if you call this as a signal basis towards representation.